Hi, this is Duncan Ferguson. In this unit we're going to talk about the adrenal cortex physiology, specifically relating to the synthesis of adrenal steroids by the adrenal cortex. In this slide we depict the adrenal histology in sort of a cartoon fashion, starting from the outside with the capsule, and where you see there's blood flow coming into the adrenal gland, and then the various sections of the adrenal cortex, which consist of glomerulosa, fasciculata, and reticularis, usually memorized as GFR, from outside to inside, and we'll get to that later. The inside here is the center, if you will, of the adrenal gland, is represented by the adrenal medulla. That'll be handled in a separate unit. But as we go from outside to inside, we have glomerulosa, which makes mineralocorticoids, then the fasciculata, which makes mostly glucocorticoids, so that's why it's capitalized, and some sex steroids. And then we have the reticularis, which make mostly sex steroids and some glucocorticoids. And then, of course, the medulla, which makes catecholamines. Before we go into more detail on their secretion, let's just talk about the general role of glucocorticoids and mineralocorticoids, the two major products that we're going to talk about from the adrenal cortex. First, I think you may have heard and are aware of that the glucocorticoids are one of the several hormones that produce during stress, the others being epinephrine and, of course, ACTH, which actually is there to stimulate from the pituitary, stimulate the glucocorticoid secretion, as we'll talk about later. But over general aspects of physiology, the glucocorticoid role is to sort of drive metabolism, and we'll talk about all of these in much greater detail later, and also to be involved in water balance, and mostly with regards to volume. Okay, so they're involved in keeping the volume within the extracellular fluid. And the major glucocorticoids are cortisol in most of our species, and some of the rodents we see the corticosterone. Mineralocorticoids, most species we see aldosterone, and its major role is to influence particularly the balance of sodium and potassium. Talk about that more later. And of course, secondarily, blood pressure. Although I don't want to belabor structures here, I think it is very useful to note that these hormones are derived from cholesterol. You can see the cholesterol structure right there. But note that very tiny differences between the glucocorticoid cortisol and the mineralocorticoid aldosterone is seen primarily at this site here and this site here. If you compare the two, and these tiny differences in structure can lead to significant differences in the types of receptors that these hormones will bind. They're small and they're lipophilic. The molecular weight for most of these are around 300, and this means that they can penetrate membranes, obviously with a cholesterol-like structure, and we'll talk about later, being lipophilic, they're not very happy by themselves without some help in circulation in an aqueous environment. In this complex slide that we have here, we will talk you through it. Basically, it's important to sort of look at the top, and first of all, as we pointed out in the previous slide, to note the role of cholesterol as a precursor, right here, and then an enzyme that's got various names, but one of them is side chain cleavage enzyme right here, is impacted by the pituitary hormone ACTH in a positive way. So that first step from cholesterol to the next product, pregnenolone, right here, is a rate-limiting step and particularly controlled by ACTH. So what you can see with the rest of this schematic, and I encourage you to spend some time just sort of looking at it from the standpoint of its logic with regards to relationships between these hormones. You'll see that when we later on talk about drugs that impact adrenal cortical secretion, some of these target the enzymes we're going to talk about. So if you start with pregnenolone, and then you look at what it can happen to it. Basically, it can be either 17 hydroxylated to 17 alpha hydroxypregnenolone, which then is subjected to the 3-beta hydroxysteroid dehydrogenase. You'll see it's over here also. Well, that's why we'll say there's a parallel pattern here. And as this product, 17 hydroxypregnenolone, can either go to the androgens, you'll see that here, or they can go through down to 17 hydroxyprogesterone right here, and then be 21 hydroxylated to 11 deoxycortisol, and then to 11 hydroxylated to cortisol. So look at the relationships. This becomes very important in certain kinds of diseases of the adrenal gland where we see some of these products being increased and some not as increased, and yet there's still adrenal gland dysfunction. So that's going to the glucocorticoid side over here. And then on the right side, we have, you can see from pregnenolone, we have 3-beta hydroxysteroid dehydrogenase forming the sex steroid progesterone and 21 hydroxylase. And then that takes it to 11 DOC, 11 deoxycorticosterone, and then the 11 hydroxylase to aldosterone. So these are the two pathways from our glucocorticoids and mineralocorticoid. So to summarize in this slide, ACTH has got a major action on the adrenal glands and particularly on the adrenal cortex and stimulates the zona fasciculata and reticularis from the standpoint of it being trophic. That means it can hypertrophy or plump up those sections of the adrenal cortex. And secondarily, of course, it's regulating the secretion and production and secretion of both cortisol or corticosteroids and androgens. Major step that's regulated by ACTH is the side chain cleavage enzyme, which is regulated by ACTH. And because ACTH is secreted in an episodic fashion, we'll talk about that. Secondarily, so are glucocorticoids, and that leads to pulsatility to the glucocorticoid concentrations in the bloodstream. So we said that glucocorticoids are lipophilic, and it's important to point out. Because of that, they're not happy in aqueous environments like the circulation, and so they need to be carried by plasma-binding proteins to improve their solubility and also even distribution. What are these binding proteins? Well, we have the general, relatively low affinity, high capacity, non-specific albumin, which is obviously can be competed for by other compounds that are small molecular weight, like the glucocorticoids. But more specifically, we have corticoid binding globulin, CBG, which binds about 75% of the cortisol at any given time. And then of the remainder, this is the active, biologically active form, according to the free hormone hypothesis, and that is about 10% of the cortisol, for example, is free and therefore active, available to the tissues for action, and of course also degradation, metabolism and degradation. So the important thing to recognize that this is a reversible equilibrium, shown here in this equation on the bottom, that the binding is non-covalent. That means that it can go on and off, and this is sometimes hard to understand, and it's defined by an equilibrium constant. in a solution, but constant on and off allows the enough free hormone to be available to all the tissues at any given time, and yet still make it through and be bound most of the time, 90% of the time, if you will, and be carried throughout the body. So what happens to the glucocorticoids once they are out in the circulation and approach tissues such as the liver? It's important to recognize that they can be conjugated with great efficiency to glucuronic acid, basically adding on to the glucocorticoid. And these conjugates, that's what they're called, biliary conjugates, they can re-enter the circulation and then be excreted, or they enter the biliary tree, and they can be excreted by the kidney and via the biliary tree via the feces. And why is this relevant to us as clinicians? Well, we use, not uncommonly, urinary cortisols in the diagnosis of hyperadrenocorticism because they correlate with plasma cortisols. And they also integrate over a period of time. And we also, in animals that it's very difficult to get a blood sample or that we don't want to stress them and we want to understand either their sex steroids for reproductive purposes or even their glucocorticoid levels over a period of time for the purposes of evaluating stress. As we mentioned, cortisol is a stress hormone. We can measure this in the feces of zoo and wildlife animals. And this is actually done. So in summary, the adrenal cortex is composed of an outer histological zone that produces mineralocorticoids, that's the zona glomerulosa, and two zones, the fasciculata and reticularis, that produce glucocorticoids and sex steroids. And remember, we're going to remember this by the acronym GFR. The sex steroids are derived from cholesterol, and its conversion to pregnenolone is part of the rate-limiting step of synthesis. I'm not so worried that you understand the actual name of that enzyme, but that you understand that ACTH is absolutely crucial to this, and this is driving this sort of coordination from the pituitary, the anterior pituitary, to the adrenal gland, what's going on here. That once these lipophilic hormones, molecular weight about 300, are secreted, they have to be carried, and we have a relatively high affinity binding by the corticoid binding globulin, CBG, and that these hormones, when secreted, are also can be metabolized and put into the feces and urine, and we can use measurements of these excretions to help us evaluate an animal's status, usually for sex, reproductive status, in the case of androgens or progestins or estrogens, and also corticoids with regards to the possibility that they're under chronic stress.